Now the final polysaccharide for today is cellulose. Cellulose now is funny because cellulose is made up of beta glucose. Good. Cellulose is made up of exclusively beta glucose molecules. Now the trick is the beta glucose molecules, remember that the OH is at the top. Because the OH is at the top, it's going to create a problem to form the glycosidic bond. So if you notice where I have the OH at the top here, this other OH and carbon 4 is at the bottom. So the glycosidic bond cannot be formed there. So what we have happening is that we have a flipping of every other beta glucose molecule, and that flipping means is that we're going to turn this 180. So let me just do that in the video. So what I mean by a flipping now is that I'm going to remove this, put this down here, put this O here and the C here. So if I put the O here and the C here, this OH going to go up here now and the H down here. Seen? So that's what I mean by when I flip the molecule. In other words, it's just like, in other words, if I set my hand like this and this, my thumb represents carbon 6. So if this is carbon 1, beta glucose, so my carbon 6 is up there, so you use the carbon 6 to keep a track. So this is carbon 1, not carbon 1 but glucose, beta glucose 1. For the second beta glucose, the carbon 6 will be down here. Good. And then for the third one, it goes back up here, and then for the fourth one, it goes down here. So that to that to that, look at them. Carbon 6 I have up there, flip it down here, and then I flip it again and it's up there. I know the greatest thing that you guys need to remember is just that the molecules for the beta glucose have to be alternated. So this is a simplified version of it. So carbon 6 up top, notice for the next one it's down the bottom, then for the other one it's up the top, and then for the other one it will be down the bottom, and it continues just like that to ensure that the glycosidic bonds are able to be formed. Now for not for carbo but for cellulose, you have all of these chains, cellulose chains lining in a horizontally and parallel to each other. So when I say horizontally and parallel to each other, they are like this. So you have one chain up there, then another chain down here, and then you have another chain down there. Good. So you end up having your glycosidic bonds being formed just like that. The same thing down here. But what happens is, because these two molecules are so close to each other, they actually have hydrogen bonds being formed between each of the molecules. So you have cross linkages. So it's like you have two things like this, make it 3 or 4. Good. And then you have linkages between them. So it's like a piece of fiber cloth, and then you're stitching them together. So they run parallel to each other, they have cross linkages, and they form fibrils. Now these fibrils group together into larger groups and they form fibers, right? That's the fiber now that makes the cellulose as strong as it is as a polysaccharide. So I'm going to review now. Alright, to summarize, I'm going to send the picture of this table in the group and the notes. To summarize, we for polysaccharides, we're going to summarize some features about the polysaccharides. So we're looking at 3 polysaccharides. We look at amylose, we look at cellulose just now, and then glycogen. The features that we're going to look at is, first we look at the monosaccharides that build these polymers. We're going to look at the types of glycosidic bonds. We're going to look at the shape, and then we're going to look at the bonding, the hydrogen bonding in the molecules, look at the solubility in water, and finally look at their function. So let's look at amylose first. If you recall from the, don't remember which video, but in the video you can recall that the glucose unit that makes up amylose, we said it was alpha glucose units. Good. So it was made up of all alpha glucose units. And the types of glycosidic bonds, it was a 1,4. So this is an alpha 1,4 glycosidic bond that was present in the amylose. The overall shape, remember I said that the shape was a helix. So we can write a helical shape. It's a helix. I just write helix. You can write helical shape for it. It's not linear, right? So we can write helix. I'll probably give you a better name afterwards. For the hydrogen bonding, is it within the molecule or between the molecules? It's always going to be within. So the hydrogen bonds exist within the glucose molecule. Solubility in water, this is going to have a low solubility. So as it relates to solubility, remember, because the hydrogen bonds are within the molecule, that leaves very little opportunity for water to form any bond with this molecule. So in terms of solubility, it's going to be very, very low. Even if we are digesting this molecule, you need an enzyme. And I don't have to ask people, if you look at the name of this molecule, you will know which enzyme breaks this molecule down. Because all we need to do is to remove that O and put an A, and you will know which enzyme that is. Good. So down to break these glycosidic bonds, alpha 1,4 bonds, you're going to need amylase, right, and some water. Good. So in terms of the solubility, because the hydrogen bonds within the molecule, it becomes very low. The function here is going to be so low solubility, and it is an energy reserve. Good. Energy reserve. Let's look at glycogen now. Glycogen, what type of monomers make up glycogen? Everybody would remember alpha glucose, just the same. Glycogen is made up of alpha glucose molecules. What types of bonds, glycosidic bonds, would you see in alpha glucose? In glycogen, you would see both alpha 1,4 and alpha 1,6, because remember the bonding is what? The side chains. Remember this video where I spoke about the side chains right here that makes this molecule glycogen. Good. So that's why we would have alpha 1,6 and alpha 1,4 to make it glycogen. In terms of the overall shape, we could use spiral. I added spiral for amylose, so we could use spiral with branching. Good. So the spiral have branches off them. Look at it. See it? The branches come off. Good. The hydrogen bonds is going to be within, and the solubility is going to be low as well, because the same reason we give for amylose is the same reason here, and it's also going to serve as an energy reserve. Final one is cellulose. So if you remember, I said cellulose is made up of beta glucose units, So the beta glucose units is what make up cellulose, and you're going to have beta 1,4 glycosidic bonds. This is linear in terms of the overall shape. Remember, I show you this, that you have parallel, horizontal parallel cellulose glucose units lined up just like that, parallel, and you have the cross linkages. So the overall shape is going to be linear. All right, as it relates to the hydrogen bonds, it's going to be within and between. Good. So it's going to be within and between the molecules. Look again. We said that you have the hydrogen bondings. Hydrogen bond is going to be within these molecules here, but it's also going to be between them. Just like I talk about the cross linkages, that's where the between comes in. That gives it extreme strength, and therefore the function of it would be structural. It'd be a structural molecule because it helps to form the cell wall and so forth. Solubility would be, it is insoluble basically. Insoluble. Good, because all of the hydrogens are bonded in within and between, so there's nothing there for the water to latch on to.